So we are very happy to have Yacine Mehtar from Brookhaven National Lab on the topic of the unification of Gluon distribution at small and moderate x. Please, Yacine.
Yeah, thanks, Max. So I'm very happy to be here again. Well, although not personally, but by spirit. I'm in Santiago, and yeah. So I will talk today about some new project that I started with Renaud Boussard, who is postdoc at BNL currently, and it's related to trying to understand connections between small x regime of QCD and moderate x. So typically the Bjorken limit and the Regge limit. So these are two regimes of QCD that are somehow that have been studied very extensively since the 70s, and there are little work. Let's put it this way: a little first principle work that tries to connect these two. It's a very challenging problem. All right, so why this now? First of all, I mean, there is a lot of work recently that focused on trying to cure a problem that was recognized in small x physics. So the equations that govern the evolution of the structure functions and Gluon distributions at small x are known as the Balitsky-Kovtchikov equations, and that describe the Gluon distribution in the saturation regime. And this was calculated up to next to leading order. But the next to leading order shows some numerical instabilities. Now it is understood and it's solved, but there are still some open questions, and I will try to somehow put this in perspective with the Diglop evolution equations and try to see whether we can find a different way of solving this problem. So, so this is the outline. So I already mentioned that I will talk about the BK equation, and then I will say, well, this is basically the line of thought we had with Renaud. So why do we have a problem in the BK equation? And what is the problem with small x physics? So we talk about small x, but what is x in small x? What does x stand for? So that's the Bjorken x in DIS. We think in terms of Bjorken x, but the question is what do we really mean? Does it appear naturally when we calculate the observables at small x? Then I will start somehow developing the strategy, and along the way I'll have to introduce new objects in small x physics, which are transverse gauge links. Then I will revisit the most important approximation in small x physics, which is the shockwave approximation, which simply uses the fact that the target that you probe in high energy collisions is Lorentz contracted, and you assume that so the longitudinal extent, it goes to 0. So that's the shockwave approximation. So I will revisit this, find a different way of tackling that approximation, and then apply it to DIS and show that if you do this, you see the appearance of a new object that somehow interpolates between small x and moderate x. Okay, so a few words about the different regimes of QCD here. So x is the longitudinal fraction carried by partons in, say, in the proton, and q squared is the hard scale of the process, and basically it relates and it is conjugate to the resolution, the distance scale at which you probe the proton. So you see here in this 2D plot here the different regimes. So if you fix x, which is basically fixing the energy, so you see it here, x is related to q squared over s. If you fix the energy, then and you vary the resolution, by increasing the resolution, what you see inside the proton is more and more partons, gluons, and quarks that have smaller and smaller transverse sizes. So this is how the picture of the proton evolves, by varying the resolution scale. But of course, in this regime, the proton is still a dilute of objects. So the quarks and gluons, they are weakly interacting, and they simply don't. So you can still describe them as independent partons. And this is the parton model. So the partonic picture is natural here as you have weak interactions. Now at small x, it's different. So small x, say you fix q squared and you go this way, you go vertical. So you go smaller and smaller in x. So what happens is that the transverse size of your partons doesn't change, so the resolution is fixed, but their number would increase, and in fact it will increase dramatically, and it will be dominated by gluons. So in this regime you will have a lot of gluons, but at some point, because of unitarity, there will be saturation of the number of gluons, because as you can see here, gluons will start overlapping, and you will have nonlinear effects such as gluon recombination, which lead to the saturation of their number. So this is a nonlinear effect, and the partonic picture somehow breaks down here. You'll have to resort to a different description. So the evolution equations that describe this evolution in X is BFKL equation, which is valid in the regime where saturation is not yet achieved. So you have more and more gluons, but they're still in a dilute regime. At some point, you'll hit a boundary, which is called the saturation boundary, which is characterized by saturation scale. Oh, sorry. Okay. Let me go back. So there is a saturation boundary, which increases with the saturation scale increases with x, and you can see here this is by increasing x here, the saturation scale increases. So the hope in the early days was that at small enough x, the saturation scale can be large enough so that we can use perturbative techniques to tackle this weak coupling techniques to tackle this non-perturbative regime, because you have to account for nonlinear effects. All right, so let me. So I will of course discuss here in this talk DIS. I will focus on inclusive deep inelastic scattering for simplicity, and because this is enough to convey the message. So what is the spirit of DGLAP and how it shows up when you look at deep inelastic scattering? So what is deep inelastic scattering? I mean, probably you all know about this. So you take an electron, you look at electron-proton collisions. So the electron will exchange a virtual photon with the proton, and in QCD, the way you see this process is via this leading order diagram, where you exchange a photon with one of the quark constituents in the proton here. So that's the leading order diagram, and you see that this piece here. So I'm not showing the electron. That's the leptonic part, but the hadronic part is completely characterized by the momentum transfer here and the energy of the proton. So the momentum transfer is, you have negative virtuality, it's q squared, and then you have the Bjorken x. So Bjorken x is defined as q squared over 2p dot q, and if you define S being the center of mass energy of the photon-proton system, then Bjorken x is q squared over S. So the proton is moving in the minus direction. It's a high energy proton. You can choose a frame for the photon that moves in the opposite direction, the plus z direction. Here we use the light cone variables. And in this regime, in the Bjorken limit, which is the limit where q squared goes to infinity, then you can neglect transverse momentum transfer between the proton and the projectile here. And if you do so, the leading order diagram, you can see that in fact the Bjorken x equals in fact the longitudinal momentum fraction carried by this quark here, and this somehow gives this natural picture of picking up a quark that the leading order diagram. This partonic model, somehow partonic interpretation, gives us the picture that basically you're interacting with a quark with a certain fraction of the proton momentum, and then of course you convolve this with the probability that you pick that fraction here, and that's the parton distribution function here. So this is the leading order, and at leading order in partonic, this distribution doesn't depend on q squared. Now you can evolve this, calculate next to leading order and high order corrections, and in doing so, first, you will recognize that there are mass singularities, which corresponds to gluon radiations that will be collinear to the quarks in the in the Proton wave function, and this leads to large logarithms. These are collinear logs. So even though you assume that the coupling constant is small, this could be enhanced by phase space factor here, which is a log, and if Q is large, and mu would be some factorization scale, but typically we have in mind a non-perturbative scale such as lambda QCD, then you can have a large enhancement. This means that this is no longer a small contributions, and this will have to be resummed. So you'll have to resum ladder diagrams such as this one. So you'll have multiple gluon emissions. You can have also somehow quarks going this way and exchange with gluons. So the leading log accuracy, successive emissions are strongly ordered in transverse momentum. So you start with non-perturbative scale here in the Proton, and then the transverse momentum will increase along this direction all the way to Q squared, which is the hard scale of the process, which is the virtuality of the photon here. Now you have a strong ordering. That's where the leading log will live. That's how you get the DGLAP logarithm. But then if you look at the other variable, which is x, which is basically k minus, this is longitudinal fraction, again, of the proton carried by the quark here, then you realize that this regime of DGLAP, we already have the strongly ordered transverse momenta, is given by basically k minuses of similar order, which are of order of the root of s. So all of the k minuses here, there are no strong ordering, they're of similar order. So k minus is typically the universe formation time here. So all of those interactions happen roughly at the same light cone time here. All right, now we have k perp, strongly ordered, k minus, which is related to the x, Feynman x variable, which are similar order along the ladder, but then k plus, which is the other final variable. If you use the mass shell condition, k plus is k perp squared over k minus, then using this ordering here and the fact that k minus is not strongly ordered, then you get a strong ordering in k plus. So k plus is strongly ordered and in fact decreases from the photon rapidity here down to the proton rapidity. So this is an important observation because this ordering will happen also at small x. Now, let's see what happens at small x. So small x, that's the Regge limit, and in the Regge limit, q squared is assumed to be much smaller than s. So this gives you an x which is much smaller than 1. And that's described by the BFKL equation. So what is the phase space now? Now you generate large logarithms of the rapidity, and in fact it's log of 1 over s, because now q squared is not really generating any large logs. And of course, in this regime, you are dominated by gluons. So you have the splitting function, gluon splitting function, has this soft singularity which the quarks doesn't have. So you can ignore to leading order the quark degrees of freedom, and you'll end up having only gluons. But of course, gluons don't interact with the photons, so you'll have to at least have this to leading order the interaction of photon with the quark, and you get this this kind of interaction of photons splitting into a dipole and then interacting with the gluons in the target. Now, the ordering variable here is k plus. And as I said here, this is a consequence of this phase space. You have an ordering in k plus, and you have the same here. So k plus is ordered. So now it's ordered from square root of s down to some non-perturbative scale along the ladder. So it's decreasing. And of course, and k perp is assumed to be of the same order. So there is no ordering in k perp because there's no log generated. There's no collinear singularity. So the consequence is that k minus is strongly ordered. So k minus now, so k plus decreases from the photon to the proton, and k minus increases. K minus increases, meaning that the maximum longitudinal fraction minus is of course carried by the proton, so it has to increase in this direction. So you see, so the pictures are different, but there is a DGLAP evolution. You resum collinear logs in the BFKL, you resum rapidity logs, but they have one thing in common, is the ordering in the k plus variable. So these are the two pictures, one applied at moderate x, when s is of order q squared, and one applied at small x. So now, if you want to deal with saturation effects, then you have to introduce new tools. So you can, of course, do perturbation theory and use Feynman diagrams to calculate somehow order by order your observable. But there is, of course, a more systematic way of tackling this problem using Wilson lines. So at small x, the relevant degrees of freedom are strong classical fields. So typically you assume that the gauge field that describes your target, here A minus, again, because the target moves in the minus direction, so the component of the gauge field that's somehow dominant is the minus component. And because you have a strong field, remember we have a lot of gluons, of course, they generate a strong field at small x, then, and the coupling constant is g, so this is of order 1, so you'll have to resum multiple exchanges, multiple interactions with the target. And because the k plus component is small, this is the eigenvalue approximation, and also the k minus is small compared to the energy, square root of energy, then this can be described by the so-called Wilson line. So this is a path-ordered Wilson line in the plus direction, in the direction of the photon. So it goes from minus infinity, meaning that the interaction starts at minus infinity, and then you have an exchange of arbitrary exchanges of gluons in the T channel here, and this is resummed in this gauge link here. So x plus is again the direction of the quark propagation here. So now if you go back to the diagram that I showed before for BFKL, here now your leading contribution will come from a photon splitting into QQ bar. So this splitting can happen. So the interaction here is almost instantaneous. The interaction with the target is almost instantaneous. So that explains why you have the minus infinity here. So the splitting happens at arbitrarily early times compared to the time scale of the interaction here, which is of order 1 over the square root of energy. And then that's the approximate, the shockwave, the so-called shockwave approximation. So because it goes like 1 over the square root of energy, it can be assumed to be instantaneous as compared to any other process subsequent or prior process to this to the interaction, which in this case here is splitting. So the splitting happens at early times, and then you have a synthetic interaction, and then the quark antiquark goes back into a photon here. So the interaction here is described by two Wilson lines. One that describes the color precession of the quark, and the other one is the color precession of the antiquark. And then if you connecting color here, because it's a color singlet, then you get this object here, which is the trace of the Wilson line at the certain transverse position x1 for the quark, and of course the U dagger for the color precession of the antiquark. And then this is measured in the proton states here. And this is the building block for QCD evolution at small x, and in particular in a saturation regime. So this is a dipole scattering amplitude, which plays an important role, as I will discuss, in the in saturation regime. All right, so I mentioned some problems at next to leading order, but before that, let me just say a few words about the how we starting with this leading order description of scattering processes at small x, how this would evolve at high orders. So this is given by the Balitsky-Kovchikov equation. So this equation will describe the nonlinear evolution of the dipole scattering amplitude that I just introduced as a function of rapidity now. So rapidity being log of q plus over some factorization scale lambda plus. And this is simply, this simply will resum those large logarithms here, which somehow are a consequence of the strong ordering in the q plus variable. So here's again our dipole scattering amplitude. Now, of course, the Wilson line depends only on some transverse coordinates, but you'll have to assume a factorization. That's how this rapidity will enter the game. Now, given this, you can calculate higher orders, the next to leading order correction, and you focus on the leading log. And simply by radiating a gluon, the gluon now will be radiated off the quark or the antiquark, and then goes through the shock wave and this happens at certain transverse position z, and you get this equation. So you generate, this interaction will generate two dipoles. So a dipole made of basically this the gluon and the quark, and the gluon and anti-quark, and this is given by this term here, which is this quadratic term. This is the nonlinear part, and then of course you have by unitarity requires to subtract the contribution of the non-interacting dipole here. All right, so now this is the variation with respect to the rapidity, and you get this nonlinear evolution equation, which, as you can see, there's a fixed point when s goes to 1, then the right hand side goes to 0, which means simply that this is where saturation happens, when the S matrix here goes to 1. Now you go to next to leading order. What happens? So I'm not showing the equations, but this was done, and the equations are known, and they were put on a computer. And what happens is that the equations are not stable, and they lead to negative so instability, negative values for the dipole amplitude, and this was a little bit, in fact, somehow poses some questions about the validity of such an equation. But in fact, this was known early for the BFKL in the late 90s, and this somehow was adapted to the next to leading order BK, in particular, where so the solution was adapted to the BK, and as I will show here. So how can we cure this? First, what is the origin of such instability? Well, the origin is the fact that so there is no x, in fact, in our description. So Feynman x doesn't appear naturally when you do the shock wave. So the only thing we have is this rapidity that somehow connects q plus variables, and x is related to the k minus or q minus variable, not the q plus. And in fact, the evolution of the dipole scattering amplitude doesn't depend on x. So what happens at next to leading order is you see that for two gluon radiations here of similar k minus, there is a phase space for large transverse logarithms to appear. So this happens when this, say you have a dipole here, this fluctuation x1, small dipole that radiates a large dipole, or in other words, a gluon that is collinear to the antiquark here radiates a gluon at much larger transverse momentum. So x1 is much more than transverse position x2, and this may lead to large collinear logarithms. And in fact, this is somehow reminiscent of Diglap evolution. When you have a k minus of the same order, then you expect to see large collinear logs. You can live with this, but the problem is because you have larger logarithms, the next to leading order, there is some possibility that this next to leading order may be larger than the leading order, and in which case you have to resum such a contribution. So in fact, another way of looking at this problem is through the formation time. So because small x doesn't really connect to the x variable, which is related to formation time, again, the x minus, you end up at leading order integrating over an physical region of phase space, which corresponds to k minuses, k minus 1, which is larger than k minus 2. In fact, it has to be smaller because you have an ordering information time, but because you don't somehow keep track of your x, then you may have integration over an physical region of phase space, which is k minus larger than k minus 2. And this somehow is another way of looking at the problem, and also leads to another solution to this problem by Guillaume Buffier, who simply implemented a constraint, somehow kinematic constraint to leading order to solve this, to resum those collinear logs. So there's another solution put forward by Duclos et al. To this problem by resumming those collinear logs at next to leading log. All right, so can we live with this? Why not? So there are solutions, as I just said. You have the kinematic bound, you have resummations, but first of all, they spoil the renormalization picture established at leading order. In other words, you have to do something at next to leading order to make your somehow equation work. And this nice picture for renormalization that you had at leading order somehow breaks down in next to leading order, because you have to do this resummation to cure the problem. Of course, to all orders, then it works again, because you resum to all orders, then you have this picture. But perturbatively, it seems that this is this picture is breaking down. Then it exhibits some scheme dependence. The way you resum your logs will lead to some scheme dependence, as observed in this work here by de Gluon et al. The other thing is, this solution is based on really resummation techniques and Feynman diagrams. So there is no operator definition that may allow us to have systematic order by order calculation. And the other point is that this was discussed only at the level of the evolution equation for the dipole scattering amplitude, and was not discussed at the level of observables. And in fact, to discuss factorization and renormalization, you need to put this in perspective with a certain observable and prove certain factorization before you can really claim that you have an order by order this description of your evolution equations. All right, so this is just to show that although there is a solution and the equations is under control now, it's somehow we can still try, this somehow is pointing to a deeper problem that might be solved differently. And this is the point of this talk. So where is X hiding then in the in small x physics? So as I said, in the shockwave approximation, you assume that your target is infinitely somehow contracted to zero longitudinal extent. And so the standard trick, again, to make X appear in DIS, for instance, is to say that, well, the rapidity that I introduced, which is log of Q plus over Q plus over some non-perturbative scale here, is simply related to log 1 over Bjorken X. Of course, that's a bold relation, but it's valid to leading log accuracy. If you ignore and neglect somehow collinear logarithms, then to leading log, that works. All right, so you see here, this is just to recall the factorization formula for in high energy scattering. So you have here a dipole wave function, which is described by this phi squared. This is the splitting Altari-Lipari splitting function here, which describes just how the Q plus is shared by the quark and the anti-quark system here. And then, of course, you have your dipole scattering amplitude. And you can see, we know that the cross sections depends on Q squared and Bjorken X. And on the right-hand side, we see that the dipole scattering amplitude depends on this rapidity, which is not directly connected to X Bjorken. So to somehow try to dig deeper in this mismatch between X and Y, let's see if what do we get when you take the collinear limit. So collinear limit meaning that if Q squared goes to infinity, I expect to see DGLAP, DGLAP somehow one loop DGLAP kernel corresponding to gluon going into Q to a quark. So that's what I see. So here there's a gluon exchange here. So I expect to see a gluon going to a quark splitting function for that enters the DGLAP evolution equation. So how I do it? Well, Q squared goes to infinity. Here it is. Q squared goes to infinity, and Q squared is conjugate to R. So Q squared goes to infinity, meaning R goes to 0. So meaning the dipole goes to infinitely small transverse sizes. And what should be done now is, so we should simply expand in gradients for small r. If you do that, so the Wilson line, which is measured as a certain impact parameter plus the dipole size here, just expand it. You have a gradient expansion. And you have this derivative of the Wilson line that appears. And in fact, the derivative of the Wilson line here, acting on the Wilson line, which is in fact an object that accounts for multiple interactions in the longitudinal direction x plus, here it will act on one of the fields inside the Wilson line, and you get this derivative acting on the field, but then which will be dressed by two Wilson lines, one going from minus infinity. So there's here a typo, should go from minus infinity to x plus, and then x plus, and then x plus to plus infinity. So you have two gauge links that will dress this object. But then this object, you recognize, in fact, the field strength tensor. So you have this object field strength tensor, which is natural in description of when you do operator product expansion. And this is how you will interpret this as somehow a transverse gluon that is exchanged with the target. So in doing this, then you recover well, you think you recover the Parton distribution, the Gluon Parton distribution function. So this expansion here, you get some R squared. So this is simply what you would expect. This is the color transparency factor here, and then you get the unintegrated Gluon distributions up to R to the fourth power corrections. Now, what's the problem? So I said we recover the PDF, but of course the PDF has to depend on X, and X is K minus over P minus, but there is no K minus on the right hand side. So I get my F here, FF. I have two gluon exchanges here, dressed with Wilson lines to make it gauge invariant, but then I have to evaluate this at certain rapidity, which is connected to the plus component of the momentum of the photon, but there is no X appearing here. Let's somehow contrast this with the actual gluon Parton distribution function, and which is given here. So what's the difference? So apart from simply the averaging procedure here, you can always, so I'm explaining here that basically the additional integration here about the impact parameter and the y plus can be simply canceled out by the proper normalization of the distribution. But the key difference is this phase. In small x physics, x goes to 0, so there's no dependence on x. So this phase is simply set to 1. There's no phase. But for moderate x, when x is not small, then you get this phase, which is simply acting as a phase that appears in a Fourier transform that connects the longitudinal distance here, this non-local structure here in x plus, to the in fact the Bjorken x here. Well, here it's Feynman x, and this disappears here in the small x approach. So again, just a few words here about the structure. So you have two, you measure two gluons here, transversely polarized gluons, that are described by this field strength tensor, which are connected by gauge links, which are those gauge links here, Wilson lines, which like Wilson lines that make sure that this object is gauge invariant. All right. So when is x, small x physics and valid, and when we expect it to break down? So as I said, you have the phase, and the phase, if you assume that the target has a longitudinal extent, which is of order 1 over p minus, which is 1 over root of s, then you look at the phase, and the phase is of order x being again the Feynman x. So in the shockwave approximation, we assume that there is a strong ordering in x. So Bjorken x is much smaller than the Feynman x, meaning the gluon x, which is much smaller than 1. And if this strong ordering is satisfied, then one can neglect the phase. That's basically the phase space for BFKL and BK. That's how you get the large logarithms, soft logarithms, rapidity logs. Now, x is an integration variable here. So we'll have to integrate over x. And there is a phase space for this integration where x is close to 1, even if x Bjorken is small. And in this phase space, you expect to see large collinear logarithms when q squared is much larger than lambda QCD. And this is where the DGLAP lives somehow. Okay, so as I said, if you are at leading order, this is not so important. But as we know, when you go to next to leading order, the typical collinear logarithms become important, because you start looking at regions where two radiations have similar x, and that's where you see large collinear logs appear. All right, so how much time? Okay, so all right, so let me just a few words about how we describe the target. So the target here can be in the small x limit. The target can be described by classical gauge field. So, and this gauge field is can be solved, can be extracted by solving the Yangel's equations in any gauge, and you can show that it's basically a minus in covariant gauge, and also in light cone gauge A plus. So you have here a boosted target that moves on the x minus, and then it will be described by the A minus component. Then, of course, you can derive a more general solution by simply gauge rotation. So you just apply gauge rotation on your field, and then you generate the transverse gauge field, and this is how you get a more general solution, which involves an A- component and a transverse field component. Why doing such a transverse rotation? It's because the partonic picture is manifest in the gauge where A- is 0, but in small x, if you put A- to 0, then there's no other field and everything is 0, so trivially 0, and then it's, of course, nonsense. So, of course, putting A- to 0, this means that you'll have to generate a transverse field, and that's the correct Lightcon gauge, which makes the partonic picture appear. So that's why it's useful to reformulate small x in terms of transverse gauge field, so that we have the connection with the partonic picture natural. So this is just some digression, just to show that we can do that as a first step towards the connection with moderate x. So the transverse gauge field appears naturally simply by looking at the Wilson line and observing that the Wilson line can be parallel transported from a certain position x2 to x1, and in doing so, you generate a transverse gauge link. So the dipole scattering amplitude that is made of two light-like Wilson lines in the plus direction can be completely rephrased in terms of a transverse gauge link that runs along at x plus minus infinity, which runs in the transverse plane here. So this allows a connection between somehow the formulation in A minus equals 0 gauge and A plus equals 0 gauge. All right, so you can do better, and then you can use the non-abelian Stokes theorem, and you can realize that this contour here for this is a gauge link. This is again the light-like Wilson line here. The quark, anti-quark, you have a transverse gauge link, can be completely formulated in terms of a surface integral here of that involves the so-called twisted field strength tensor, which are just field strength tensor that are dressed with Wilson lines, which are pointing to infinity. So these are, as you can see, these are the building blocks, and this is to all orders in twist expansion. And you see the appearance of this field strength tensor even in the dipole scattering amplitude with Wilson lines that make it gauge invariant. This is just a way of showing that we can build objects that to all orders in power of powers of 1 over q squared, which make the natural object that appear in twist expansion appear here in small x. All right, so now let me go into the actual problem, or at least the way we would like to solve this small x problem and connections with the moderate x. So we thought that maybe the problem is the problem is related to the fact that from the outset, when we set the problem in the small x, we completely ignore any connection between longitudinal dynamics and transverse dynamics. So we take S to infinity, we get shock wave, and the transverse momenta are completely decoupled. What we do in practice in this shock wave approximation, we take the propagator here, and then we say, well, the propagator can be described here by basically this Schrödinger type equation. So this is the kinetic term, which accounts for the quantum diffusion in transverse space. And then you have the interaction with the field. So what do you do? Well, you say, well, P plus goes to infinity, regardless of any value of this transverse field here, transverse momentum here. So P plus goes to infinity, P plus being somehow related to 1 over square root of S. Then you, by taking P plus to infinity, then the transverse coordinates will be constant here. So you will have a constant, the propagation will be on a constant transverse coordinate. So X perp equals to Y perp. And then you get a Wilson line, somehow color rotation that is generated by the propagation. So that's the only effect of the propagation, the color precession, and that the transverse coordinate doesn't change. So now you can question this P plus to infinity. This is what we are going to do here. So first of all, as I said, we neglect quantum diffusion. Even if you have transverse momentum that is not a transverse coordinate that doesn't change during the propagation, you still have quantum diffusion, and quantum diffusion can be important. This is the free propagator, can be important when the transverse distance that is explored by the particle in the shock wave here, which is conjugate again to x plus over p plus, and you see how you connect the transverse coordinate to any change in transverse space is connected to p plus. So if you take p plus to infinity, you are assuming that this transverse change is much smaller than any variation in longitudinal space divided by p plus. So this is the assumption in shockwave. But in fact, this is not somehow required. And you can, in fact, relax this approximation and keep this quantum diffusion, which become important when this somehow condition happens here. So if you keep this phase, this quantum diffusion, then this will encode the information that was lost in small x, which is the information about the k minus in the target. So this is expected to play a very important role when we go away from the strong ordering region. As I said in the beginning, the strong ordering at next to leading order, the large collinear logarithms are generated by regions where k minuses are not so strongly ordered. So how do we do this? So we go back to the shockwave. We say, well, shockwave, one of the consequences of the shockwave is that the transverse coordinate is not doesn't change. All right. So let's take this as an initial point, a starting point, instead of consequence, taking p plus to infinity and then get that the transverse coordinate is constant. Let's first assume that the transverse coordinate is constant, and then we perform a twist expansion or gradient expansion around that constant x. So we take x being simply the average value of transverse coordinate, initial and final transverse coordinate, and then just expand around this point, the propagator. So you expand the propagator. Now you get a free propagator. So that's the quantum diffusion part, which depends only on the difference. And then you have the Wilson line that depends on the average position here. So, and then plus higher order terms that are suppressed. So the first point I would like to draw your attention to is that you have a factorization of variables. So you have a factorization between the x variable, which is the average position, and the difference. And the difference, that's the difference that will that somehow will connect to the longitudinal dynamics. And of course, this propagator, this x minus y, is much more than x than this capital X. And this is peaked somehow, strongly peaked around x minus y, very small. So you can say that this is, in fact, this is kind of a representation of a delta function. So if p plus goes to infinity, then you recover the shock wave because this is again a delta function, but this is not necessary again. And by keeping this phase here, you will actually, in fact, keep track of the longitudinal dynamics as one would like to. All right, so this is this is now kind of revisiting the shockwave approximation. We have found a way of keeping a track of the k minus or the x plus dependence of the propagator, and then let's apply it to inclusive DIS and see what we get. So here again, we calculate this diagram here. We have a photon splitting QQ bar interacting with target, and then we'll work in we make three approximations. So we'll assume ordering in K plus because we know that ordering in K plus is common to DGLAP and BFKL or BK evolution. We assume a gluonic target, so we neglect quark in the proton, and then we work in leading power in K perp squared over S. This means that we assume that S goes to infinity, but we allow ourselves to be in a regime where Q squared can be of order S. Okay, so this is the first assumption. We will factorize somehow the target fields from the quantum fluctuations by implementing some kind of factorization scale. Any fluctuation that has a k plus larger than this factorization scale would be calculated order by order in perturbation theory, while anything that k plus below lambda then this factorization scale would be assumed to be part of the target here. And technically, I mean, because of this approximation, the a minus won't depend on x minus, and then this is simply reflected in the Fourier space by a delta function k plus, meaning that the momentum transfer, the k plus transfer, is negligible with the target. This is simply another statement for of this separation of scales here. So again, strong ordering in k plus, because we know that this is common to small x and leading to a Stieg lap. All right, this is again saying what I just said, that we work in the approximation with k perp is much smaller than s. This encompasses both limits. When s is of order q squared, this is the Bjorken limit. You have higher twists which are suppressed like kt over q, and we want to neglect this because we want to work at leading twist and Bjorken limit. And in the Regge limit, this is suppressed by powers of the energy. All right, so we want to go beyond the shock wave. I introduced this approximation. Now we want to. So what is the shock wave now? So we in the shock wave limit, we assume that the shock wave is simply somehow peaked around 0, as you can see here. Then you integrate the fluctuations here from -infinity to 0, and then from 0 to infinity. But now we want to keep some information about the longitudinal structure of the shock wave. But now, how do we define the longitudinal extent of the shock wave? So what is it, in fact? So it's still shock wave, but we still need to define this. So this is the solution we came up with, is to say, well, let's define the shock wave by the first and the final interaction. So we pick the first interaction with the shock wave. That's the first gluon exchange. That gives us a time which defines the initial, let's say, edge of the or boundary of your shock wave, and then the final interaction will define somehow the other edge. And then you have 4 diagrams. Of course, you could have this interaction could happen on the quark or on the anti-quark, and then the same for the final time. And then you have 4 contributions, and this looks a little bit involved, but in fact, it's somehow hiding a structure. And the structure that is hiding is this, again, this field strength tensor. The interaction with the quark here, and it happens at the transverse coordinate x, and the interaction with the anti-quark, which happens at another transverse coordinate, can be combined as follows. This difference, in fact, it can be written as an integral over the transverse position z, which interpolates between these 2 positions here. And then this is an integral over the field strength tensor that could happen anywhere between these 2 objects. So in fact, you start with 2 terms, and then this can be rewritten as an integral over a straight line trajectory in transverse plane of the field strength tensor. You can do this for both sides, and then the 4 terms will somehow shrink into 1 term. And this introduces somehow a more general object here and a single term, which accounts for both transverse dynamics and longitudinal dynamics. So you have a longitudinal extent. So you have this kind of gauge link structure where you have a transverse gauge link here at the that connects the y at time x1 plus. This transverse gauge link will connect y1 to x1, and in between you have this field strength tensor. The same for the last time, and then in between here you have propagators, non-iconal propagators that depend on the momentum of the quark. It's not yet fully factorized formula, but this is the let's say the first object that appears before doing any approximation on the let's say any iconal approximation. This is a really non-iconal operator. And just to show you that, in fact, this operator appears naturally in this framework that's beyond iconal, without really spoiling the standard picture we have at small x. So we still have the same wave functions that appear in small x. So kind of similar factorization, except instead of having the dipole scattering amplitude here, you get this dipole operator that is non-local in transverse space and also in longitudinal space. The other important point, is that you have the phase that gives you the dependence on Bjorken x. That's because we're treating the longitudinal phase space, longitudinal variables correctly. The other point is that this is you see here in the dipole model here, the transverse, the calculation, the observer is local in transverse space. So the wave function is evaluated the same transverse separation for the dipole as the dipole. So everything is local here. But here, when you introduce the x dependence, then this this kind of locality in transverse position space disappears. And this was observed already some time ago by Bialas, Navley, and Peshansky, where they tried to enforce an x dependence in the dipole model, and they concluded that this was somehow that the dipole model was inconsistent with an x dependence, because dipole model requires local somehow locality in transverse space. So it's kind of you might then conclude that somehow we'll have to somehow give up on this locality if we want to keep track of the x dependence, and indeed this is what we have to do. Okay, so this is the final part of my my talk. So I showed this kind of rather complicated operator, but I haven't yet applied the revised shockwave approximation, so we can make it even simpler. And this leads to new unintegrated Gluon distribution. So again, I perform my last assumption, working assumption. I expand around the fixed transverse coordinate in the shockwave, and I get my Wilson line, and I get this quantum phase here. And then I introduce two new variables. One is again x, which is conjugate to well, this u, the separation, the small u here is separation, the transverse distance explored by the propagation, which is conjugate to the transverse momentum of the quark and the or the anti-quark, while this x will be conjugate to the dipole distance, as you will see. All right, so now we'll move to momentum space, and in momentum space, then the phase appears naturally. So combining all of the phases, the conjugate variable here is again to the distance here, which is L, which is again the transverse momentum of the quark and antiquark. You will have a phase associated with quark, phase associated with the antiquark, and the phase associated with the photon, and you combine all of them, then you get the phase that you need to have to connect to the Feynman X. That's exactly the same phase that you would see in the Dirichlet limit, in fact. If you were to calculate the leading twist Dirichlet, you would get this phase here. All right, so we have this x dependence, and then we've applied this kind of shockwave approximation, and then we get this formula here. So what do we have here? So we have again the same wave. I write it in momentum space because it's somehow more explicit in terms of showing the how the Gluon distribution appears. So what you have here is again the same wave functions for the splitting and then the merging here of the QQ bar pair. The transverse momenta here are simply transverse momenta associated with the quark and antiquark pair, and the K is associated with the momentum transfer in the T channel between the target and the QQ bar pair here. So this is all similar to shockwave. Now the difference is that now you have an explicit x dependence, which correlates Bjorken x to the kinematics of the QQ bar pair here. And this is given by this delta function. So now we have kind of solved this mystery of connection between Bjorken x, the left-hand side, and the right-hand side. Then you get this Gluon distribution, which is not very different from the dipole distribution, but it has this structure here. So now we have this kind of rectangular shaped gauge structure. So you have again the same gauge links here, the light gauge links, and then you have transverse gauge links, and which are connecting two field strength tensors that we need to integrate over. And somehow this gives us also, although this has no relation with Parton model, but you can see when you take the distance here, this psi perp to 0, then you get back the PDF. So you get the PDF very easily. So the PDF just take integrate over k-perp, you get psi perp to 0, then you get the PDF, and then this is exactly the structure you would get for the integrated gluon distribution. Now, if you take the small x limit, so neglecting the phase, then you are contracting this tensor structure with the corresponding structure here, then you get back the dipole. So you have the two limits that are encoded in this gluon distribution, which enters this factorization formula. So this is the conclusion somehow. This last slide just to show that there's a minimal approximations that one may, or a minimum modification of the shockwave approximation that lead in fact to the appearance, an explicit dependence on X, which connects to naturally to the Bjorken limit, which is moderate X as it should be. And we believe that this, if you go to next to leading order, this will in fact also cure the problems that we see for next to leading order BK evolution. Okay, so let me summarize and give some somehow outlook for future work. So we have revised the shockwave approximation. So we have presented the new prescription for how we can take this shockwave limit without keeping also a connection between transverse and longitudinal dynamics by keeping this accounting for the quantum diffusion. So this accounts for both limits, small x and moderate x. So we expect that the evolution of that Gluon operator would lead to somehow a DGLAP evolution would connect DGLAP with the BK evolution. So we looked at DIS. So we have shown in particular that we get the factorization formula that involves a new unintegrated Gluon distribution, which again accounts for naturally and easily for the different limits, known limits. And for the outlook, we plan to tackle the quantum evolution and see how this would connect to, how we can connect to the DGLAP and BK equation. And we want to look at other observables like DVCAs to investigate the universality of this distribution. Is this distribution universal or not? And the last point is the following. Because we have a distribution that is bounded in longitudinal space and transverse space, then we can hope to use this Gluon distribution to probe saturation on the lattice. And that would be, if that works, then we'd have somehow we would have a direct measure of saturation scale. If we see it on the lattice, then that would be would confirm somehow the existence of such a regime, which is still elusive in experiment, which it's not yet achieved, and it's not even clear whether we can achieve high enough energies to probe that regime. And this is it. Thank you.